All right, we're going to do the very last section of the chapter. It's 5.9, linear programming. So we can wrap this chapter up and do a test on it. So what is it? What is linear programming, and how is it relevant to the real-world situations? So now we're actually going to apply what we've been doing with the shading with inequalities to a real-world situation. We're only going to do one problem. So let's get to it. One problem. It's going to take us a while, though. Example 1. For the small company Cuddlesoft, a bed sheet requires 2 pounds of cotton. Oh, by the way, I'm going to go through and underline everything as we go through it. So 2 pounds of cotton, 9 minutes of dyeing time, and 2 minutes of packaging time. So this is for a bed sheet, just to be clear. A set of pillowcases requires 1 pound of cotton, 12 minutes of dyeing time, and 8 minutes of packaging time. So all that for a pillowcase. Each day, Cuddlesoft has available 20 pounds of cotton, 180 minutes of dyeing time, and 48 minutes of packaging time. So we're looking at this small company, and we're looking at how much of everything they have. They're using cotton, and they only have so much time to package things. Oh, and also dye them different colors. Okay, so with all that information, we're going to go ahead and create some inequalities to graph on this number line, or on this coordinate plane. So part A, let x equal the number of bed sheets made per hour. All right, so just remember that x is the number of bed sheets, and y is the number of sets of pillowcases made per hour. We're going to find the vertices of the feasible region for pairs xy the company can make. So before we do any of that, we have to create inequalities, then put them on the coordinate plane, figure out where to shade, and then eventually we'll be able to find the vertices. Okay. So I actually helped you listed out all the ones that we're going to do for the inequalities. 1, 2, 3. There's going to be 5 of them here. So let's go through and remember that x is the bed sheets and y is the sets of pillowcases. So we're going to create inequalities. So let's go through it here. We have cotton, the available cotton inequality. So if we look at this, we're going to look at the cotton stuff. I'm just going to highlight it. How big is that? Okay. We have 2 pounds of cotton for the bed sheets, right? We have 1 pound of cotton for a pillowcase. And the total amount of cotton we have for each day is 20 pounds. So I'm going to make an inequality with those numbers. I'm going to say 2x, because it's 2 pounds for a bed sheet, plus 1 pound of cotton for a pillowcase, 1y. You got to remember that x is bed sheets, y is pillowcase. And the most we have is 20 pounds of cotton. So is it going to be equal to 20? Well, no, because it is possible to use less than 20 pounds. So that would mean that if we add these two together, we want it to be less than or equal to. We can use all 20, but we cannot use more than that. So it's got to be less than. All right, now the dyeing time. Let's change the highlight here. Ooh, how about green? So let's go through the dyeing time. So the bed sheet requires 9 minutes of dyeing time. The pillowcases require 12 minutes of dyeing time. And how much do we have each day? 180 minutes. So same idea. 9x for the bed sheets, plus we have to add how much it costs or how much it takes for the pillowcases. 12y. And we have a total of 180 minutes. Again, we cannot use more than 180. We can use exactly 180, but it has to be at least 180 or lower, not more. So less than or equal to. All right, we have another one to go through. What's red look like? That works. Packaging time. The bed sheet requires 2 minutes of packaging time. We have pillowcases require 8 minutes, and the total for each day, 48 minutes. So the inequalities would be 2 minutes for packaging, so 2 minutes for the bed sheets, 2x, plus 8y for the bed sheets, and that's going to be at most 48 minutes of packaging time, but you can go under, so less than or equal to. These are all less than or equal to. All right, the last two inequalities, it says the least values for x and least values for y. So think about the fact that we can't use anything less than 0, right? If we're going to make bed sheets, a number of bed sheets, it's not possible to make a negative number of bed sheets or pillowcases. So x stands for the bed sheets. So what I'm going to say here is that x, the number of bed sheets, has to be bigger than or equal to 0. We're allowed to use 0 bed sheets. We could just make all pillowcases, but it has to be bigger than or equal to 0. Same thing for the y's. That would be your pillowcases. You can use 0, but hopefully we're going to use more than 0. So we're going to say y is also, we want that to be bigger than or equal to 0. What this does here is really just highlights the fact that we don't want to go outside the bounds of the y-axis or the x-axis. It's all going to be positive numbers here. So that's what this takes care of when we actually graph it. So let me start with those two, and I'm going to highlight them on the graph here. Do I make it a little bigger maybe? I could do that maybe. Okay. So least values of x. So the bed sheets want to be bigger than or equal to 0, so I'm going to go ahead and just write that on here. So this line here, straight up and down, we want it to be positive numbers. So this line here is x is greater than or equal to 0. Ooh, that's fat. Same thing with the pillowcases. It has to be bigger than or equal to 0, so that's highlighting this line here. This would be your x-axis. Let's turn it down a little bit. So this would be y is greater than or equal to 0. And I think I'll erase this too. Just rewrite it. That actually just takes care of the axes. We're saying, hey, we got to be bigger than both these. So we're going to shade this way for the y-axis, and then we're going to shade above it for the x-axis. But that's all we really have to shade. It just takes care of any negative numbers. Okay, now we can do the other things. First, we got to figure out, we got to label these. It said x is the number of bed sheets, so I'm going to put bed sheets down here. Number of bed sheets. And then the y value is the number of pillowcases. Number of, oh man, pillow cases. All right, you get the idea. I think every single block will be 1. So I don't know if you can see like the darker ones here. Every 5 is marked. So I'm just going to label it. There's 5, 10, 15, 20, 25, 30. So we can get up to 30 for each one. X and Y, 5, 10, 15. Wait. Oh, we can only go to 20. Sorry, only 20 this time. But that should actually work out okay. I'm going to graph these. So whenever I'm going to graph these ones, I'm actually going to do the shortcut. This is going to be unfortunate. But if you remember the shortcut, remember labeling these like A, B, C? I'm going to do that to get the X and Y intercept, and then I'll draw the lines. So to do the first one, we're going to do the X intercept, which would be C over A. If you remember these shortcuts. That's 20 divided by 2. 20 over 2, which is 10. So the x-intercept for the available cotton is 10. I'm going to change colors too. Let's do red. X-intercept is 10. That's down here. 10. And then the y-intercept is C divided by B, if you remember. That's 20 over 1, or 20. There we go. 20. So its x-intercept is 20. Now, if you use a ruler, you can draw a straight line. Mine is going to be terrible, but oh well. That's going to be bad. Oh boy. There we go. Perfect. These all also are solid lines because there's equal there. All right, next one. Let's go to the green. We'll do a shortcut again. A, B, C. C over A, oh, it is pretty bright, is 180 divided by 9. That's 20. So this is the x-intercept is 20. That's right here. Y-intercept is C over B, which is 180 divided by 12. That's 15. So the y-intercept is 15. Put a dot, and we'll connect them. Oh, jeez. I overshot that. Try it again. A little better. So I'm going to actually have to cheat a little bit because these are not going to work out. You have to draw nice straight lines. This is not going to work out for me. All right, the black one, changing to black. We'll do the x-intercept. We're doing the packaging time. C over A would be, A, B, C. 48 divided by 2. That's 24. And we'll throw that in for the x-intercept, 24. Right here. There we go. The y-intercept would be 48 over 8. That's 6. Remember, that's C over B. Y-intercept would be 6 right here. So this one's fairly slanted. Oh, no. There we go. There we go. Perfect. All right, and we already talked about the last two. We're saying we're shading above 0 on the x-axis and the y-axis. That's what these two are. And then all these other ones are less than or equal to. Now, you could do test points of 0, 0. So if I were to go back for the red one, this would be 0 plus 0. Oh, man, come on. 0 plus 0, because you plug in zeros here, is less than or equal to 20. Is 0 less than 20? Yes, it is. So you'd be shading below the red. I'll just put an arrow or two. Below the red. Same thing with the next one. You plug in zeros here. 0 plus 0. See what's going to happen every time. Is less than 180. Sure is. So we're below in the green. And then the last one would be the black one. Okay. 0 plus 0 is less than or equal to 48. These are all really easy test points to use. And that's obviously true, so it's less than this. So everything gets shaded below all the lines. As you can see, where's our final place where they intersect? It only looks like it's like this bottom part here. So I'm going to shade this. See how this looks. Like this. There we go. We're above the blue lines, but we are below the other ones. The black, the red, and the green. Really, the green doesn't seem to matter. Only my red and the black lines seem to matter. Okay, so now we're done. We have the feasible region. We're going to be finding the vertices of the feasible region, but I'm going to first, I guess we can label them, can't we? The vertices of the feasible region, we have one on the y-axis. That would be 0, 6. We have the origin, believe it or not, that's where the two blues intersect. That's 0, 0. Come on. And we only have one, or no, two more. We have the x-axis here. That is, I believe, 10, 0. And then we have this intersection point here, and it's supposed to be, now I didn't draw it correctly, it's supposed to be 8, 4. If you use a ruler, hopefully you got that. Let's put a big red one there. This is supposed to be 8, 4. On my graph, it actually looks like it's probably closer to 9, 3 or something, but it's actually 8, 4. Use a ruler and you'll be able to figure it out. So those are 3 or 4 different vertices. We're going to be using them in a second. So there is a theorem about this. It's called the linear programming theorem. What we just did is technically called linear programming, getting this feasible region, the vertices. So what it says is, when you have the feasible region of any linear programming problem, it's always convex, which just means it doesn't have like a dip in it or a dent in it. Don't have to worry about too much about that part. And the maximum or minimum quantity of what you're trying to find is always going to be determined at one of the vertices of the feasible region. So in our particular case, I'll wait a second. If you want to find, I'll go back here. If you want to find the maximum or the minimum value of our situation, that's always going to be found at the vertices, at one of them. So choosing any of the values on inside here doesn't really matter. It's not going to maximize or minimize. In this case, we're going to talk about profit, how much money you make. What we all care about is the vertices. That's going to give you the maximum or the minimum value. So then we're going to continue this problem and do like a part B with it. So we're going to look at the equalities that intersect to make the feasible region. So the vertices were, if I remember, it's 0, 0. We had 10, 0, 0, 6, and 8, 4. Those are all the vertices. Now we're going to be looking at those to answer the next part. So here's all 4 of them. 1, 2, 3, 4. All right, part B. The company's hourly revenue is $12 for each bedsheet, $8 for each pillowcase. Assuming they sell everything they make, how many of each product the company produce per day to maximize the revenue? The only way you can figure out to maximize the revenue is by testing the vertices that are around the feasible region. First, they actually gave us kind of an equation to use. The revenue equation is how much money profit they're going to make. So I'm just going to say P equals profit. Or we can use R for revenue. It doesn't matter. R for revenue. R is equal to the revenue, how much money they're going to make. They get $12 for a bed sheet. I think bed sheet was X. Plus, for every pillowcase they sell, it's $8. So 8Y. So we're going to use this this equality now, and we're going to test our vertices. So I'm going to test each vertex. So we have 0, 0. That's not going to give us much money, right? We have 12 times 0 plus 8 times 0. Clearly, that's not going to make the most money. In this case, this would be $0. Not a lot of profit. But remember, this linear programming theorem says the vertices give you the minimum and the maximum. Minimum and the maximum. So that must be the minimum value. The next one we'll do is 10, 0. So that would be R equals 12 times 10 plus 8 times 0. That would give you $120 plus 0. So that's all that would be. So we're making some profit. That's if we just did all bed sheets. Third one, 0, 6. I keep writing. I don't need to write out 0, 6. R equals 12 times 0 plus 8 times 6. That would be 0 plus 48. So the revenue there is only 48. Not as much as we want, not as much as the 120. And the last combination we had was 8, 4. So the revenue is $12 times 8 bed sheets, plus 8 times 4 pillowcases. So that would be 96 plus 32, and that is $128. So it happens that the most money you could possibly make is $128, and this is the combination. So the most profitable vertex is, we'll say, 8 bed sheets with 4 pillowcases. and that is for $128. So that is how you would get the most money out of all the constraints you had with the dyeing time, the packaging time, and how much cotton you had available. That's it. That was one problem. Last thing we'll do is some fill in the blanks. So this is actually used in all different kinds of companies. It's heavily used where competitors make the same product, like gas, phones, like cell phones, appliances, clothing, all that stuff. So many companies would use something like this. All about maximizing the profit of things that they're making. Pretty much any company would need a linear programming problem with all the different constraints to figure out how to make the most money. Their efficiency is in use of labor and materials. So if you're paying somebody money per hour and how efficient you can be with the materials that you have, that affects your profits. These situations in real life can really involve way more variables than we even looked at. You can have up to 500 variables and 10,000 inequalities all at once. Most likely you would not be doing them by hand, but you would have some kind of computer program that you could put the numbers in and figure out. We just scratched the basic surface of figuring out a profit problem that we just did, figuring out the revenue. So for the huddle, all we have is one problem to do. It says 1 to 5, but it's broken up into one problem to different parts. It's the same thing we just did, all the same stuff, just a different problem. And that would wrap up chapter 5 with 5.9.